So, in this video we are going to discuss one important algorithm for the heap data structure, that is Max-Heapify. So, in the Corman book the algorithm name is Max-Heapify, and some other books you can find the same algorithm with different names, like some authors have named this algorithm as adjust, some other authors have given like bottom up Heapify or top down Heapify, like this, but the algorithm is same. And if you understood this Max-Heapify, then the alternate, that is mean Heapify, is similar to this. So, before moving to the algorithm, we want to discuss two properties or two attributes of a heap data structure, and these two attributes are like this. So, one is a dot length. So, where a represents the heap. So, we know that the heap is represented by an array, and here the name of the array is a. So, a dot length means, so the number of elements in the array. So, number of elements in the array A. Similarly, another attribute is there, that is a dot heap size. So, here what is heap size? So, the size of the heap or number of elements in the heap are stored within array A. So, two different things, one is a dot length, another one is a dot heap size. So, this a dot length represents the number of elements in the array A, and a dot heap size represents number of elements in the heap that are stored within array A. So, we know that the heap size, a dot heap size, so always less than equal to a dot length. So, it can be equal or less than. So, the heap size always less than equal to a dot length, and it is larger than 0. So, you can write like this one. So, 0 less than equal to a dot heap size, less than equal to a dot length. So, we can write the relation in this way. So, the array elements are a of 1, 2, 3. So, like this, a dot length. So, the indexes are like this. So, here these a of 1, 2, 3 up to a dot length contains the elements, and the a of 1, 2, 3 dot 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 a dot heap size are the heap elements in the array. So, this represents a of 1, 2, 3 up to a dot heap size represents the number of elements present in the heap, and this a of 1, 2, 3 up to a dot length represents the number of elements in the array, and from this array a dot length, a dot heap size up to a dot heap size are valid elements of the heap, and some of the elements from a dot heap size to a dot length are present in the array, but not the elements of the heap. So, if we write like this, we can write like this. So, the elements from A dot heap size plus 1 to A dot length are present in the array. So, the elements A dot heap size plus 1. So, this is heaps for heap size. So, you can remove this space if you want, hyphen if you have any confusion. Also, let me rewrite this one. So, we can say like this: A of A dot heap size plus 1 to A dot length are the valid elements. So, the index of the elements A dot heap size plus 1 to A dot length are the valid elements of the array, but these are not in the heap, or the elements do not belong to the heap. So, I hope this one is clear. One is A dot length, another one is A dot heap size. So, heap size means number of elements present in the heap, and A dot length is number of elements present in the array, or we can say A dot heap size is the number of elements belongs to the heap and stored in the array A, and you can find this relation. So, now we will move to another property. So, like this, here we can consider. So, if a full binary tree, so I am writing this one, has n nodes, so number of nodes are n, then its left subtree and right subtree has maximum n by 2 nodes. So, we will see one example of this. So, I am not going into the mathematical details. So, we can see one example. Suppose one element is, suppose the full binary tree is like this. So, this is a full binary tree. So, number of nodes here you can say n. So, it is 7 number of nodes are there. So, 3, 4, 5, 6, 7 total 7 nodes are there. So, then its left subtree, suppose we consider this node. So, its left subtree has 3 nodes and its right subtree has 3 nodes. So, here you can see. So, how we are getting 3? So, 7 division 2. So, it is 3. So, we are ignoring the fractional part. Now, I hope this one is clear. So, I am not going into the mathematical details or mathematical proof. So, we will move to the second one, second property. So, if a complete binary tree has n nodes, then its left subtree and right subtree has maximum left subtree, or you can consider right subtree. Okay, so you can consider and or, so no issues. So it is, you can consider this or, has maximum 2n by 3 nodes. So we will see one example. So the formal proof is out of scope of this course. Suppose consider this one. So we have a tree like this. So it is a complete binary tree. So how many nodes are there? So here you can see 7 for 11 nodes are there. So if we remove this one, or if we consider this node, then its left subtree has how many nodes? 7 nodes. So left subtree has how many nodes? 7 nodes. And in the right subtree has how many nodes? So right subtree, if we consider 3 nodes, this one is the right subtree. If we consider this one as the root node, so this one is the left subtree and this one is the right subtree. So in the left subtree 7 nodes, so you can apply the formula 2 into n means 11 by 3, so 22 by 3, so it is 7 point something. So we are ignoring the fractional part, so it is 7. So maximum 2n by 3 nodes are there, or 2 into n by 3 like we have written here. So maximum 2n by 3 nodes can be possible for complete binary tree, and for full binary tree it is n by 2 nodes. So this one is also a complete binary tree, but this is a special case. So maximum for complete binary tree 2n by 3, so it can be n by 2 also. So this one is also a complete binary tree, this one, but here n by 2 is there. So if we consider among n by 2 and 2n by 3, so this one is maximum, so this is the upper bound. So for complete binary tree 2n by 3 maximum number of nodes are possible in the left subtree or in the right subtree. So now we will move to the Max-Heapify algorithm. So now we will discuss about Max-Heapify algorithm. Max-Heapify algorithm. So this algorithm is used to maintain the max heap property. So here this algorithm is used to maintain the max heap property. So to maintain the max heap property, we use this Max-Heapify algorithm. And what are the input to the algorithm? So the input to this algorithm is the array A, so that represents the heap data structure, and one index I. And here in this algorithm, or this algorithm assumes that the left subtree of I and the right subtree of I, or we can say right of I. So to represent right subtree, I can write right of I. So this left subtree of I and right subtree of I are max heaps. So the input to this algorithm is an array A and one index I, and this algorithm assumes the left subtree of I and right subtree of I are max heaps. But A of I, A of I might be smaller than its children. So left of I and right of I are max heap, but A of I might be smaller than its children. So that's why the max heap property is violated at A of I. So here violating the max heap property. Max-Heap property. So the input to this algorithm is array A and index I, and we are assuming that in this index I the Max-Heap property is violated, but the left of I and right of I, or the left children of I or left child of I and right child of I are Max-Heaps. So here at index I the Max-Heap property is violated. So this is the assumption and input. So using this Max-Heapify algorithm, so we'll put the element A of I in its correct position so that the Max-Heap property is satisfied. So this algorithm Max-Heapify puts the value of I, puts the value or element value of A of I, because A of I violates the Max-Heap property. So this algorithm Max-Heapify puts the value of A of I in its correct position, in its correct position, so that the Max-Heap property is satisfied, so that the Max-Heap property is satisfied. So now we'll see one example, then we'll write the algorithm. So we'll see one example for this. So assume the heap or the max heap is like this: 16, then 4, then 10, so 14, then 7, then 9, then 3, then 2, then 8, then this is 1. So if I want to write the index of these elements, so it is index 1, it is index 2, it is index 3, 4, 5, 6, 7, then 8, 9, 10. So the red color, in the red color I am writing the index, and the blue one is the value of the elements. So here you can see this node or this element 4, or in this tree or complete binary tree, or in this heap, here at index 2 the max heap property is violated. So here you can see 4, its children 14 and its children 7. So the element 4 is less than its children, and if we want to put this element in its correct form, then what we will do? So that is the Max-Heapify algorithm. Assume the array name is A here, because we represent this tree in an array. So assume this array name is A, and the index where the property or Max-Heap property is violated is 2. So this A and 2 will be the input to the Max-Heapify algorithm. So in real life scenario, or without discussing the algorithm, so or without going into the formal steps of algorithm, so how we can put this element in its correct position? So here you can see this 4 is less than its child 14 and 7. So which element, if we compare this value 4 with the child elements, so which one is largest among the children? So 14 is largest, so here you can find 14 is largest. So 14 should be here and this 4 should be here. So we are going to just swap these two elements, or swap the parent and child here. So after swapping, so the new element will be, so here let me remove the index part. So the index part is not required. Now okay, so it is 1. Okay, so now if we consider this subtree, so here you can see 4 is violating the Max-Heap property, and among the children 14 is highest, so we want to swap this one with its parent, or 14 is going to swap with 4. So here this 4 becomes 14 and this 14 becomes 4. Now when we swap, so again you can check, so let me remove this old value 4 here. Okay, old value 14 here, so I am removing. So now, so we can write this properly as 14, so 14, and we can write this one as 4. So after one exchange, so now we can check, when we put 4 here, this violates the Max-Heap property again, because here you can see the left child is 2, right child is 8, and this parent has less value than its right child. So what we will do, again we will swap here. So if we swap, then here in place of 4 8 will come, and here in place of 8 4 will come. So now we can remove this part for better understanding. So here is 8, here it should be 4. So we can move this 8 properly to here and move this 4 here. So now you can observe 4 is there in its correct position and the Max-Heap property is satisfied. Here you can see. So all the elements are there in their correct position and the Max-Heap property is satisfied. So now we can write the algorithm. So what is the algorithm? What we have done? So the input is A and the index 2. In this example it was 2, or you can take I. So what we are doing? So first finding the largest element among the children and thus just swapping. Then again after swapping, if the subtree does not satisfy the Max-Heap property, again find the largest element and swap. So in this way we will put the element that violates the Max-Heap property in its correct position, and we proceed towards the leaf node in this way. So now formally we can write the steps for Max-Heapify algorithm. So I can write like this: Max-Heapify, and the inputs are A and I. So I is the index where the Max-Heap property is violated, and A is the array that represents the heap. So what is the first step? So in first step we have to find the index of the left child. So assume L represents the index of left child. Similarly we can write R represents the index of right child. Now in the next step we have to compare the element at index I with its left child. So how you can compare? So if L less than equal to A dot heap size, so if L value do not cross the heap size and A of L greater than A of I, then we can say largest is L. So if A of L, that means the left child value is greater than the parent, so we can say largest is the left child. So this thing we have written. Else, it means if this condition does not satisfy, then we can say largest is the root. So this thing I want to write here. Else largest is the element that is at index I. Now in the next step, so in step 6, we want to compare the element that is at index I with the right child. So the same thing we have to pair, or we have to write. So if r less than equal to a dot heap size and a of r greater than a of largest. So if a of r value, that means the right child value, is greater than a of largest, then we can say largest is r. In this way, in the step 1 to 7, we are writing to find the largest among the left child and right child. So the steps 1 to 7 just find which one is largest, it is left child or right child. So if the largest value is not equal to I, so if the largest is not equal to I, that means the largest is either left child or right child, then what we are doing, we have to simply swap or exchange, we can write. So swap or exchange a of I with a of largest. So this simple. Then again we have to apply the Max-Heapify algorithm with the index that is largest. So after swapping we have to check again. So like we are doing here in this example, first here 4 was there, then after swapping 4 comes here and 14 comes here. So here also 4 and 8, so there is a problem. So again we have to apply the same procedure considering this one at the index I. So the same thing we are going to write here. So again apply the Max-Heapify algorithm on the input A and index largest. So this is recursively we are calling the Max-Heapify algorithm here. So these are the simple steps. So first find the largest, then swap, and again apply Max-Heapify algorithm. So we are going to apply this algorithm until the element is stored in its correct position. So these are the simple steps we have to follow. So now we will move to the running time for Max-Heapify algorithm. So what is the running time for Max-Heapify algorithm, or what is the time complexity of Max-Heapify algorithm, that we have discussed just now. So here you can see step number 1 to 7 is just to find the largest among the left subtree or right subtree, or we can say left child and right child. So step number 1 to 7. So step number 8 to 9 is just swapping. So this step number, we can say this 1 to 7 is to find the largest. So this one may take a constant amount of time, or we can say this is step number 1 to 7 is theta of 1 time. So constant amount of time or order of 1 time. Now again this step 8 to 9, so it is a constant amount of time. So you can also consider this is theta of 1 time. So if we add constant amount of time plus constant amount of time, so it is also a constant. So step number 1 to 9 is theta of 1. So we can consider this step number 1 to 9 is constant amount of time. So, the steps that we have written from 1 to 9 takes theta of 1 time or constant amount of time, that means to find the largest and swap. Now, this algorithm or this step number 10. So, Max-Heapify A largest. So, again we are applying the same algorithm on the subtree. So, one of its subtree. So, if we say that T of n is the time complexity of Max-Heapify algorithm, where the number of nodes are n, then this Max-Heapify A largest. So, this will be the T of 2n by 3. So, if T n is the time complexity of Max-Heapify where n number of nodes are there, then again we have to apply the algorithm either in the left subtree or in the right subtree, and we have discussed just now that. So, here we have discussed. So, the left subtree and right subtree can contain maximum 2n by 3 number of nodes. So, if T n represents the time complexity where n number of nodes are there. So, when we apply the Max-Heapify algorithm on its right subtree or left subtree, then T of 2n by 3 time will be there or will required. So, we can write this one formally. So, we can write like this. So, T of n equal to theta of 1 plus T of 2n by 3. If we solve this T of n equal to theta of 1 plus T of 2n by 3 using master theorem, so we are going to get this T of n is equal to order of log n, and this order of log n is nothing but equal to the height of the heap. So, that is why you can write this as order of h. So, the running time of Max-Heapify algorithm is order of log n or order of height. So, I hope this is clear to everyone.